Everywhere you go, physics exists. The thing I'm here to talk about today is slingshot physics, and this one right here. Pretty much just the physics behind what works behind the slingshot. And one of the major concepts of slingshot physics is elastic potential energy. Elastic potential energy is the potential energy stored as a result of deformation in an elastic object, such as a stretching of a spring. It is equal to the work done to the stretch of the spring, which depends upon that spring constant K as well as the distance stretched. According to Hooke's law, the force required to stretch the spring would be directly proportional to the amount stretched, since the form has the form of F equals negative Kx. Elastic potential energy also seems to combine with Hooke's law, which is what a spring would follow. Now, what Hooke's law states is that the stress applied to a material is proportional to the strain on that material. For example, if the stress on a metal bar is 10 newtons per square centimeter, causes it to be compressed by 4 millimeters, then a stress of 20 newtons per square centimeter will cause that bar to be compressed by 8 millimeters. Hooke's law generally only holds up to the elastic limit of stress for that material. But the strange thing is that slingshots don't follow Hooke's law. So let's see what we can understand from observing the slingshot visually. Real time might have been too fast. Now pay attention to this slow-mo video of Anthony launching the projectile. Now, if you pay close attention, there are a couple things that are obvious. For example, if Anthony wanted to add energy to the system, all he would have to do is pull back the bands. But the thing about this is that the further he pulls back the bands, the harder it becomes to add energy to the system. So, in conclusion, the reason that slingshots, or more specifically rubber, does not follow Hooke's law is because the stress applied to the material is not directly proportional to the strain on that material. If we were to plot the potential energy going into the system versus the displacement as Lackey pulls back, because it gets harder to pull back, it is not a linear graph, instead it is a curve function. And as he releases the projectile and it begins to accelerate, it will also have a curve function. And if we were to add up the potential energy still left in the band and the kinetic energy in the projectile, they would both equal the total energy we put into the system.
Elastic potential energy is the potential energy stored because of an interference from outside the system in an elastic object. The further you pull back, the more elastic energy. The force made by the spring is directly proportional to the force placed on the spring as stated in Hooke's law. Similar to the slingshot, the more you compress, the more potential energy. The more weight, the more force. And the more force, the more elastic energy.